Warm air rises and cold air falls. It is a familiar physical rule. But inside some of Dubai's tallest cooled towers, the overall airflow can move in the opposite direction. Under peak summer conditions, hot outdoor air enters at the upper levels. Cooler internal air becomes denser and moves downward through the vertical shafts. The grand entrance at the bottom suddenly becomes an exhaust outlet. At first, this might just seem like a draft or a minor structural leak. But during a fire, the direction and pressure of that airflow become a critical smoke control problem. Where is the invisible floor that divides the tower into two pressure zones? And what happens when a high-speed elevator starts moving through it? The investigation begins with a very ordinary inconvenience. You approach the ground floor entrance of a super-tall luxury tower. As the automatic sliding doors attempt to close, they suddenly stutter and violently correct their movement. If the building uses a manual swing door, you might feel it physically fight back as you pull the heavy handle. You might hear conditioned air escaping through a tiny gap in the weather stripping. The door is not malfunctioning. It is reacting to a continuous, invisible force. To understand that force, you have to stop looking at the doorway and look up. That single door is holding back a column of cooled air that stretches hundreds of meters into the sky. How can a small temperature difference distributed over an 800-meter structure become a physical weight at one entrance? The door is not producing the pressure. It is simply the boundary where the pressure of the entire building becomes visible. The investigation begins with a very ordinary inconvenience. You approach the ground floor entrance of a super-tall luxury tower. As the automatic sliding doors attempt to close, they suddenly stutter and violently correct their movement. If the building uses a manual swing door, you might feel it physically fight back as you pull the heavy handle. You might hear conditioned air escaping through a tiny gap in the weather stripping. The door is not malfunctioning. It is reacting to a continuous, invisible force. To understand that force, you have to stop looking at the doorway and look up. That single door is holding back a column of cooled air that stretches hundreds of meters into the sky. How can a small temperature difference distributed over an 800-meter structure become a physical weight at one entrance? The door is not producing the pressure. It is simply the boundary where the pressure of the entire building becomes visible. To understand why the air is falling, you first need to look at how a standard high-rise breathes. In a cold winter climate, the heating system keeps the indoor air much warmer than the freezing atmosphere outside. Warm air is less dense. It becomes buoyant. That buoyant air tends to rise inside the building. As it moves upward, it eventually finds leakage paths near the roof and escapes into the cold sky. To replace the air it lost, the building pulls freezing outdoor air in through the lower lobby doors. The American Society of Heating, Refrigerating, and Air Conditioning Engineers defines this buoyancy-driven vertical airflow as the stack effect. The taller the structure and the colder the weather, the stronger the upward pressure becomes. The building does not need a literal chimney stack to create this draw. Its elevator shafts, stairwells, and mechanical risers already provide massive vertical paths for the air to follow. Dubai keeps the extreme height, and it keeps the continuous vertical shafts. Then it reverses the temperatures. When a super tall tower is built in a desert climate, the temperature relationship flips. Outside, the summer air is extremely hot and significantly less dense. Inside, massive mechanical plants continuously chill the environment to maintain absolute luxury. That cooled indoor air is noticeably denser and heavier than the atmosphere pressing against the exterior glass. Under suitable conditions, the normal chimney effect turns completely upside down. Engineers refer to this specific physical phenomenon as reverse stack effect. Instead of rising, the heavier conditioned indoor air may tend to drop down through the elevator shafts and escape through the ground floor lobby. Meanwhile, the highest floors may begin pulling hot, unconditioned desert air inside through tiny gaps in the upper facade. Dubai did not remove the chimney effect. Intense mechanical cooling simply turns its direction upside down. Of course, the actual pressure map is much more complicated than a simple vertical drop. It also depends heavily on wind, exterior leakage, mechanical ventilation, and open doors. But the airflow does not reverse right at the roof or suddenly stop at the lobby. Somewhere between them is an invisible boundary. Somewhere inside the tower, there is a theoretical elevation where the indoor and outdoor pressures are exactly equal. Engineers call it the neutral pressure level. In a simplified model of a cooled high-rise, the airflow behavior splits right at this invisible boundary. Above this level, the heavier indoor air drops away, creating a negative pressure that pulls hot outdoor air inside through the upper facade. Below this level, the descending column of cold air stacks up, creating a positive pressure that pushes outward against the lower doors. But this boundary is not tied to a specific architectural floor. Research from the National Institute of Standards and Technology indicates that flow areas and venting conditions strongly influence where this neutral plane sits. It can shift instantly. It moves when a mechanical ventilation system changes operation, when the exterior wind drops, or when a lower entrance is held open for too long. One open door does not merely leak air. It can redraw a significant part of the building's pressure map. For that pressure map to exist, the descending air needs a path of least resistance. It finds it inside the elevator core. An elevator shaft is essentially a second skyscraper. It is a continuous, mostly empty, vertical tunnel, completely hidden inside the occupied tower. It connects the highest machine rooms all the way down to the ground floor lobbies. But air does not just move smoothly down this single vertical tube. It navigates a complex, highly interconnected network. It bleeds through microscopic door gaps. It crosses open transfer levels. It infiltrates mechanical spaces and adjacent service zones. The shaft acts as the main artery for the building internal weather system. It carries a slow, pressure-driven airflow from the top of the structure to the bottom. It turns a horizontal floor into a porous pressure boundary. Then, a massive machine begins moving through it. When an elevator cabin descends at high speed, it behaves like a massive syringe inside a narrow cylinder. It physically displaces the air ahead of it. Simultaneously, it draws a wake of air into the empty space left behind it. This creates a temporary, highly disruptive pressure change above and below the cabin. The National Institute of Standards and Technology treats these transient pressure differences as a relevant design consideration for elevator smoke control. The force can be strong enough to push air through lobby doors and elevator gaps. This is known as the piston effect. It is completely different from the stack effect. Stack effect is the slow, continuous pressure of the whole tower. Piston effect is the rapid, temporary pressure pulse of one moving cabin. They are separate forces, but they share the same hidden shaft. Under normal daily conditions, this complex interaction of pressure and airflow is mostly an engineering curiosity. It might cause a lobby door to hiss or an elevator carriage to rattle slightly. But during a fire emergency, this everyday airflow suddenly becomes a vital safety variable. If smoke enters an elevator shaft, it does not just passively fill the space. It is captured by the pressure field of the building. Depending on the exact temperatures and the position of the neutral level, reverse stack effect could pull that smoke downward. Piston effect from a moving cabin could temporarily pump it into an adjacent lobby. This does not mean the building is inherently unsafe or that elevators automatically spread fire. It means that smoke control systems must be explicitly designed with knowledge of these invisible forces. The upside-down chimney matters not because air moves downward, but because every fire door, protected stair, and smoke control fan must know which way the building is trying to breathe. So, how do engineers stop one super-tall building from becoming one continuous air shaft? Before engineers can control the pressure, they have to map it. The engineer cannot photograph the pressure field. The engineer reconstructs it from every opening the building pushes or pulls against. They measure the physical force required to pull a lobby door open. They track the differential pressure across fire barriers and stairwell entrances using specialized digital manometers. They compare the behavior of the vertical shafts during different seasonal extremes. During structural commissioning, they may use controlled tracer smoke in closed zones to visually confirm the exact direction of air movement. They run complex computational fluid dynamics models to predict how the massive volume of indoor air will behave. But the testing immediately raises difficult human and operational questions. Which door should be held open during the measurement? Are the main air conditioning units running in normal daytime mode or emergency exhaust mode? Should the elevators be moving or parked at the ground floor? Has the neutral pressure level shifted since the last test? If the pressure at the lobby is too high, is it being caused by the cold air falling, or is a mechanical fan overpowering the zone? Every variable changes the final result. The building is not fighting one static, predictable pressure. It is controlling a highly sensitive system that reacts to every mechanical change inside the walls. And even after the temperature-driven pattern is perfectly mapped, the atmosphere outside can completely rewrite it. Temperature is only half of the aerodynamic equation. As a tower climbs past 500 meters, it encounters severe aerodynamic forces. Wind strikes the exterior glass, creating a massive zone of high positive pressure on the windward facade. As that wind accelerates around the sharp corners and architectural setbacks, it leaves behind a wake of negative suction on the leeward side. The pressure is vastly different at the base compared to the highest occupied floors. This external wind pressure interacts directly with the internal stack effect. A strong prevailing wind can reinforce the downward flow of cooled air, pushing it harder through the elevator shafts. It can increase the physical load on the lower lobby doors. Alternatively, it can directly oppose the stack effect, temporarily stalling the internal airflow. It can shift the entry and exit zones, forcing air through facade gaps that normally act as exhausts. It can alter door behavior across multiple floors. It can violently move the neutral pressure level up or down the building. Temperature alone cannot predict the real airflow. The tower does not have one fixed pressure map. It has a map that changes with the weather, its doors, and the massive machines operating inside it. Engineers cannot remove the extreme height, and they cannot stop the wind. Instead, they must break the continuous airflow path into smaller, controllable pieces. A continuous vertical path of 800 meters produces a massive accumulated pressure difference. The fundamental engineering solution is to prevent the building from acting as one single unbroken tube. Designers reduce the problem by dividing the massive air column into several smaller, highly controlled vertical zones. This is achieved through heavy architectural compartmentation. They use sky lobbies, transfer floors, and separated elevator banks that do not travel the entire height of the structure. They install sealed vestibules and heavy fire-rated doors at the shaft interfaces to physically break the vertical airflow. Improved facade airtightness and controlled leakage paths keep the external weather from easily entering the internal pressure system. The Council on Tall Buildings and Urban Habitat published a specific case study discussing passive stack effect mitigation in the design of the Burj Dubai, later renamed Burj Khalifa. This demonstrates that controlling reverse stack pressure was treated as a fundamental architectural and mechanical requirement from the very beginning, not an unexpected failure discovered after construction. When a luxury visitor walks into a sky lobby halfway up a super-tall tower, they see a quiet, polished transfer space. They see high-end finishes, marble floors, and a perfectly silent corridor. But a mechanical engineer sees a critical pressure break. They see a heavy leakage barrier designed to stop the descending column of air. They see a smaller vertical zone perfectly isolated from the floors below it. They see a controlled interface designed to reset the pressure map for the next vertical zone. The pressure control strategy extends all the way down to the main entrance. A standard automatic sliding door is highly vulnerable to the weight of a descending air column. If it is held open for a large crowd, it creates a massive direct connection between the pressurized lobby and the hot street. This is why super-tall towers heavily rely on revolving doors, double-door vestibules, and precisely timed airlocks. A revolving door limits the period in which one large opening connects the indoor and outdoor environments. It continuously allows people to pass, while always maintaining a physical seal against the pressure difference. A vestibule prevents both sets of doors from remaining fully open at the exact same time under normal operation. The grand entrance is not merely a luxury architectural statement. It is a highly engineered mechanical valve installed at the absolute bottom of an 800-meter air column. These heavy barriers are required to maintain everyday comfort, exclude fine desert dust, and limit the massive financial loss of expensive conditioned air. They support the normal circulation of thousands of daily visitors, but their most critical function is maintaining the internal pressure boundary. In normal daily operation, these heavy doors protect the cooling budget. In an emergency, that exact same pressure control must protect the human escape route. When a fire alarm triggers, the building stops prioritizing human comfort and immediately shifts into a rigorous life safety pressure mode. The most important vertical shafts are no longer the high-speed elevators, but the protected emergency stairwells. Smoke control engineering relies on strict compartmentation to isolate the hazard, but physical walls and heavy doors are not enough on their own. Engineers use large mechanical fans to actively pressurize the escape routes. The National Institute of Standards and Technology identifies stairwell and elevator shaft pressurization as a primary defense against vertical smoke migration. The Society of Fire Protection Engineers notes that these high-capacity fans are designed to maintain the stairwell at a slightly higher pressure than the adjacent fire floor. If the pressure inside the concrete stairs is higher, the smoke is physically pushed back and prevented from entering the clean escape path. But this creates a very narrow, highly dangerous engineering trade-off. The mechanical pressure must be strong enough to resist the heat buoyancy of the fire, the reverse stack effect, and the external wind. However, if the fans push too much air into the shaft, the pressure pushing outward against the heavy fire doors will become incredibly intense. The doors can become so heavy that human occupants literally cannot push them open to escape. Smoke control engineering is not simply turning on the biggest fan available. It is creating exactly enough pressure to physically isolate the smoke without turning the only escape door into an immovable obstacle. The system, therefore, operates within highly precise, rigorously tested design limits. The true test of this delicate balance begins when every environmental and mechanical force changes at the exact same time. This is a hypothetical engineering stress test, not a description or prediction of an actual emergency in a specific Dubai tower. Imagine a severe operational scenario at the absolute peak of summer. The outdoor temperature is extremely high, and the massive interior is heavily cooled, establishing a strong reverse stack pressure pushing downward. A harsh prevailing wind is simultaneously creating uneven, massive positive pressure on one side of the glass facade. Down at the ground floor, multiple entrance doors are suddenly held open by fleeing crowds. Up in the tower, panicked occupants are pushing open stairwell doors at multiple different elevations to evacuate. At the exact same moment, an empty elevator cabin drops through the core, adding a rapid transient piston effect to the already chaotic lobby. Finally, the massive emergency smoke control fans activate, attempting to inject high-pressure air into this violently shifting environment. Does the invisible neutral pressure level suddenly move? Do all those open doors bleed off the mechanical stair pressure required to keep the smoke out? Does the elevator motion create a temporary lobby pressure change that compromises the escape route? Can the fans still maintain the required safety differential, and are the heavy fire doors still operable? Does the overall airflow remain within the carefully designed safety strategy? The building system is designed to answer these terrifying questions through intense mechanical coordination. The compartmentalized zones limit how far the disturbed air can travel. The automated vestibules isolate the sudden pressure drops. Sensors and variable speed fans continuously adjust to maintain the engineered barriers. The system does not miraculously eliminate every physical pressure force. It keeps those overlapping forces from combining into one uncontrolled vertical path. When a visitor steps inside a Supertall structure, they experience absolute, unbroken stillness. They glide past quiet doors. They ride stable, high-speed elevators. They walk down perfectly cool, silent corridors. They do not feel the brutal wind, the searing heat, or the massive column of air constantly trying to push its way through the structure. None of that stillness is automatic. Behind the polished marble and the quiet lobbies is a massive, highly active operating system. It relies on strict pressure zones, shaft seals, vestibules, revolving doors, and mechanical fans. It requires heavy fire doors, thousands of digital sensors, complex airflow models, rigorous commissioning tests, and incredibly strict operational procedures just to keep the atmosphere stable. The luxury is not simply the glass, the gold, or the extreme height. The ultimate luxury is that the occupants never feel the giant, invisible air column the building is constantly fighting. Dubai's tallest towers do not remain calm because the air inside them is naturally still. They remain calm because hundreds of doors, barriers, and fans force that air to follow the exact paths the engineers designed to survive. The silence inside a Supertall tower is not natural. It is engineered pressure control. Reverse stack effect is a recognized building physics phenomenon, and its actual strength varies constantly with temperature, height, exterior leakage, wind, and mechanical operation. This documentary discusses general engineering principles and does not claim that every Dubai tower experiences identical airflow patterns. References to the Burj Khalifa concern documented architectural design considerations, not allegations of current structural or mechanical failure. All fire and smoke scenarios are hypothetical engineering illustrations, not reports of an actual incident. Generic stock footage is illustrative and should not be interpreted as depicting specific building defects. This content is for educational analysis and does not replace professional engineering assessment. If you want to understand the hidden mechanical systems that keep massive cities functioning, make sure to subscribe to the channel. Have you ever felt a sudden pressure change inside a super tall building? Share your experience in the comments below.